So for our constraint analysis lecture, we want to understand how we can build a design space that meets the customer's requirements. Put simply, we'd like to end up with some sort of plot that compares various wing loading states to the thrust to weight ratio. And when you do this, you end up with a plot that represents the design space. And these lines are lines of constraint. And what ends up happening is that when you've plotted these lines, you're left with an area, a region, as your design space. This is where you can trade off different design parameters. Anything above these lines is valid, right? We'll just put an equal sign, or to the left of this line, that's all valid. And that's your design space. However, anything down and below here is not valid. These would violate the customer's requirements and therefore not meet the requirements for the aircraft. So we developed this. It's called a constraint equation, and we're going to do a constraint analysis. And for the pre-quiz and for the homework that's due, I want you to understand how this equation is developed as part of your lecture. So one of our most favored performance measures is our piece of S, or weight-specific excess power. And if you recall that weight-specific excess power was a discussion we discovered over the last two lectures. But in this terms, we want in terms of thrust to weight and wing loading. And more specifically, we're going to want thrust at sea level over weight takeoff and weight takeoff over planform area. These are the terms that we want to be able to influence the plot that we design. And don't forget, this is the exact same plot that's in JET 10 under the constraint analysis tab. So I want you to go to JET 10, look at the constraint analysis tab, and you'll see this plot there. It's also on the main page and part of the Excel video I did for you earlier. Before we go further, let's review a couple equations. You recall lift is equal to weight in slough. That one's pretty easy, but in a turn, when you're experiencing G's or there's a load factor, we said that lift is equal to the load factor times the weight times the equation CL, Q, and S. Okay, don't forget that drag was equal to what? Drag was equal to thrust, which is still CD, Q, and S. And we said that the drag polar CD was equal to K1 CL squared plus K2 CL plus CD naught. That was the drag polar. Okay. We're going to be introducing two new terms as well. We're going to introduce this relationship of thrust is equal to alpha times the thrust at sea level. And in this case, alpha is not the angle of attack. Alpha is designated as the thrust lapse rate. We also introduce weight as beta times the weight at takeoff. And in this case, beta is equal to the weight fraction. Now I'll caution you, we're going to use beta again in the next lesson, but beta will represent an angle. So just like alpha, beta, and gamma, we're reusing some of these letters, and you have to understand the context they're being used in. These are nothing more than percent changes from the original. Okay. So we wanted P sub S in terms, or we wanted to get to thrust to weight in terms of wing loading, and we're going to start with P sub S. So you recall that our P sub S equation was nothing more than the rate of climb, right? And rate of climb was velocity times the difference between thrust and drag over weight, which is the derivative of energy height with respect to time, which we defined as dH dt plus V over G dV dt. Now look here, there's weight, there's drag, and we've already discussed those two terms above. Here's thrust, we've discussed that as well. So you're going to see a way we're going to start inserting these equations we've used previously into our equation here and then derive our master equation. Let's continue. Let's start with rearranging our P sub s. So we're going to say that velocity, thrust over drag, weight is equal to dH dt, which we've derived in our earlier classes, dV dt. And we're going to start to isolate thrust. So to do that, I'm going to multiply by weight, divide by velocity, and then I'm going to move drag over. So velocity, thrust minus drag is equal to weight dH dt plus weight velocity over gravity dV dt. And now I'm going to divide by velocity, and I get thrust minus drag is weight over velocity dH dt plus, now the velocities cancel here, so we get lucky there, weight over gravity. I like when terms cancel, dV dt. I'm also going to take this opportunity to start substituting in, this relationship for thrust and weight. So, given the relationship for thrust is equal to alpha thrust at sea level, my lapse rate, and weight is equal to beta times weight at takeoff, my weight fraction, yields this equation. I'm going to have alpha times the thrust at sea level minus drag, which is equal to beta times the weight at takeoff over velocity, dH dt, plus beta times the weight at takeoff over gravity, dV dt. And as I mentioned earlier, my last step is to move drag over to this side of the equation. So now I have alpha times the thrust at sea level is equal to drag plus beta, weight at takeoff over velocity, dH dt, plus beta, weight, takeoff, gravity, dV dt. And do you recall what we had for drag up here? We had drag and the drag polar. We had drag and the drag polar. We're going to substitute those in now too. So I'll take a sidebar here, change colors. Drag was equal to C, D, Q, and S. And now we substitute in the drag polar from above, and we get drag is equal to, I'm going to move Q and S over here, K1CL squared plus K2CL plus CD0. And we still need to figure out a way to get weight in there, so we're going to represent CL in terms of weight, in terms of its relationship. CL is equal to N, W, Q, and S. We'll plug that in there. So our new drag equation is QS K1 times NW over QS. Don't forget quantity squared, plus K2 NW Q and S plus CD0. close parenthesis. Now, what did we say about weight? Weight was equal to beta, our weight fraction, times weight at takeoff. We're also going to introduce a new coefficient, weight, a CDX, which is the drag coefficient for expendables, expendables and external. I'm sorry, that's not true. It's external. External stores. Most of our aircraft, like the our aircraft like the F-35 and F-22 don't have external stores most of the time, so that term will just be zero. So we insert this and we insert this. And we're going to have drag is equal to QS K1 times N beta over Q times weight takeoff over S. I'm going to split this fraction up, but I think we can all agree that if I multiply them together, it's just like I would have if I substituted that in. Squared plus K2 N beta over Q weight takeoff over S plus CD0 plus CDX. Okay, now that I have this relationship for drag, I'm going to substitute that back into there. So I have, let me just, alpha times the thrust at sea level is now equal to QS. Everything from above. So I'm going to just simplify my work here, or my writing, plus, what did we have left? All of this. Plus beta, weight takeoff over velocity, dH dt, plus beta, weight takeoff over gravity, dV dt. Okay? Now remember, I want to get my output in terms of thrust over weight. So I'm almost there. So what I'm going to do now, I'm going to divide this whole mess. I'm going to divide each term by beta weight takeoff. Okay. What do we have now? We have alpha over beta thrust at sea level over weight takeoff. Yay, so we're almost there, right? This is what we want. That's our output. Equals QS over beta weight at takeoff times K1N beta Q weight takeoff over S squared plus K2N beta weight Q weight takeoff over S plus CD0 plus CDX. I'm going to close that bracket now. Plus, now this divides out. 1 over V dH dt plus 1 over G dV dt. Okay? The last step is going to be to simply move this over to here. So the final form of this equation is thrust at sea level over weight takeoff is equal to beta over alpha times QS over beta weight takeoff. I know there's a temptation to probably want to simplify this, but don't. Just hear me out and I'll explain why. Okay? Let's see, I'm going to change the squiggly here. K1 N beta Q weight takeoff over S squared plus K2 N beta Q weight takeoff over S plus CD0 plus CDX closed squiggly plus 1 over velocity dH dt plus 1 over gravity dV dt closed bracket. Okay, this is the final form of the constraint analysis equation, or known as the master equation. Now let me highlight a few things for you. What is this term? Well, that's rate of climb. So for level flight, this is equal to 0. What's this term? dVd. That's acceleration. For unaccelerated flight, and let's call it UF for unaccelerated flight. That's equal to 0. I want you to see the relationships of wing loading here, but it's also resting right here. It's just inverted. That's why I don't want you to try to solve this. I want you to leave it in these terms. This, and this, that's sort of our input variable. Okay? What about N? Right? In slough, N is equal to 1. And here it is again. So my point is that this equation can quickly simplify given the types of flight condition. And then of course we have our output here. So this is a function of wing loading, which is the weight takeoff over the planform area. So you're going to take this equation and put it into Excel. You're going to do that in the next video, and I will be available as needed for Q&A.